Welcome back to another Marcus Maths YouTube video. Tonight we are going over quiz number 5 in our Unit 1 limits and continuity. And today we're going to be looking limits as they approach infinity and also some more of these infinite discontinuities. Alright, make sure to like and subscribe to the channel if you haven't already. And let's go ahead and get started with these types of questions. So it's very important that there is kind of like a long way to do these and there's an easier way to do these, because with limits, as x approaches infinity, the only values that really matter are going to be our higher degree values. So constants, they don't actually really have any effect on the graph as x approaches such large numbers as any x value. Let's say x is equal to 9 million. If we're just adding 3, 9 million compared to 9 million and 3, it doesn't really do anything. So the whole premise is that we're just going to disregard these really small values and we're only going to focus on our higher degree values, or our values with our values with variables that we're going to be substituting in these very large numbers. So how a question like this would work as we approach a positive infinity, we're just going to ignore this part right here. And we are going to take the square root of this term. Square root of 16, x to the power 4 is 4x squared. So then we're just left with 4x squared over 2x squared. These two, of course, cancel out. And we are left with the value that we approach as x approaches positive infinity. That is equal to 4 divided by 2, which is 2. So this function, as it approaches positive infinity, will just approach the x value it will approach the y value of 2. Now, there's a lot more of a technical way that we'd do this, meaning that we would multiply all of these values by 1 over x to the power of 4 inside of our square root, and 1 over x to the power of 2 for our denominator. Everything would cancel out. We'd get 3 over x to the power of 2, and we would directly, for our denominator, negative 3 over x to the power of 4 for our numerator. When we substitute in x approaches infinity to a denominator, let me just illustrate that principle. This does reoccur in calculus. Let's say we have the limit as x approaches infinity of 1 over x to the power 2. We just need to know the principle. As our denominator gets larger and larger, our fraction, like in this format, continues to approach 0 until eventually, as x approaches infinity, 1 over infinity squared is simply equal to 0. So just think, 1 divided by 2 is 0.5, 1 divided by 100 is 0.01, 1 divided by 1,000. These values continually get closer to 0. So when the denominator is infinitely large, our value is equal to 0. So that's how these would work in a technical matter. You would have to multiply by these fractions to the numerator and denominator, and then directly substitute in infinity. But you would receive the same result regardless. 2 is the correct answer with this question. Okay, select the correct description of the one-sided limits of g as x is equal to 3. This says that we would need a calculator, because all we're doing is we are going to be analyzing the left and right sided limits. Let me go ahead and show the calculator, and I'll walk us through how to do something like this. We're just going to pick values very close to 3 on both sides. Let's say as we approach 3 from the right, we're going to use 3.1, and then we'll use 3.01 to kind of like get a sense of the direction. So for this example, when we substitute in 3.1, we will have 3.1 on our numerator divided by the natural log of of 3.1 minus 2, because remember, we're substituting in 3.1 for x. And then we close off the parentheses to represent the denominator. We set this equal, and we get 32.5. Now, can we take the same thing? No, we cannot. So what we're going to do, we're going to now use 3.01 to illustrate what's happening to our y values as we get closer and closer to 3 from the right side, demonstrating that one-sided limit. Okay, divided by the natural log of 3.01 minus 2, close the parentheses. And we can see as we get closer and closer to 3 from the right side, our y value is getting closer and closer to positive infinity. So it's either going to be A or B. Now we're going to approach positive 3 from the left, meaning that we're going to use 2.9, 2.99, etc. So let's go ahead and substitute in 2.9 to start off. So 2.9 divided by the natural log of 2.9 minus 2, close off these parentheses, add a parentheses, close off the denominator, we get negative 27.5. But remember, we can only determine once we have two values to see where the direction is going. This could shoot back up. So now we're going to use 2.99 divided by the natural log of 0.99. I'll just do that subtraction already. Close off the parentheses. And as we can see, we're getting larger and, well, we're getting more negative and more negative as our values approach positive 3 from the left side. So that means that the answer choice that is correct is answer choice B. As we approach 3 from the right, we approach positive infinity. As we approach 3 from the left, we approach negative infinity. Answer choice B is the correct answer. Okay, the dashed lines represent asymptotes. Which of the graphs agrees with the statement? The limit of f of x as x approaches 0 from the right is equal to positive infinity. So we're going to be analyzing the x value of 0. This function is just equal to negative 0.5, so that limit is not correct. Let's look at B. As we approach 0 from the right, so we're going to be using this part of the graph. This right side of the graph approaches negative infinity, so once again, doesn't match the limit statement. And now let's look at question C, answer choice C. We're going to approach 0 from the right using this part of the graph, and we can see that as this right side of the graph approaches 0, the y value doesn't approach positive infinity. So that means C is the only graph that agrees with that statement. Okay, another one here. We're looking at the limit of g of x as x approaches infinity this time, not x approaches 0. So as x approaches infinity, the g of x should equal negative 2. This means that we have a horizontal asymptote this time. So we're going to be looking for these horizontal asymptotes as the graph goes off to the right. As x approaches infinity, the graph is going to go off to the right. So as we can see, answer choice A, as x approaches infinity, the y value does indeed approach negative 2. As we can see, there's a horizontal asymptote at negative 2. So answer choice A is correct. Check answer choice B. As x approaches infinity, we're using the right side of the graph. The y value also approaches negative 2 for this one. And this last one is x approaches infinity. The y value approaches negative 1. So answer choice A and B are correct with this one. And now last one here. This one's simplified. Yep, we're going to check the limit as x approaches infinity. Now, once again, the simplified way to do this is only consider the highest degree, because even x to the power of 3 will still be way overshadowed by x to the power of 4. As we know, for example, if we took 2 to the power of 4 is 16, 2 to the power of 3 is 8. So the 16 way overshadows the 8. And this gets more and more prominent as the x value gets larger and larger. Now, if we wanted to prove this algebraically in an FRQ, we would multiply every single term by 1 over x to the power of 4. That way, this would cancel to 0, this would cancel to 0, this would cancel to 0, this would cancel out, and then we would just be left with 5 over 2. So the value that this irrational function would approach as x approaches infinity would be 5 over 2. Now, it's very important. When we do these negative ones, they will behave a little bit different. As now, if you get an odd power, you will begin to approach these negative values. But remember, a negative divided by negative will still be a positive. So if both numerator and denominator are these odd exponents when we substitute in negative infinity, the answer will still approach a positive number. But it's important to practice these and get this concept right, because once again, we are going to be using this multiply each term by a fraction to represent the limit as x approaches infinity of a fraction with a variable in the denominator is equal to 0. If you have any questions about this, let me know in the comments. But that is all for today. We finished this one very quickly. I'll see you tomorrow for quiz 5, and then we will get to the unit test for unit 1, limits and continuity. Okay, if you have any questions, once again, let me know in the comments. Make sure to subscribe to the channel for more of these AP Calculus videos. If you haven't already, please like the video, and I will see you soon. Goodbye.